And now, well, it's our pleasure to introduce our first speaker, Daniel Schulte, who's the leader of the International Muon Collider collaboration, and is going to give us an introduction to Muon Collider so that you motivate yourself to listen to the rest of the week.
Okay, thanks. So I'll do my best to keep you motivated. So thanks for the invitation. So today I wanted to introduce overall the Muon Collider concept, its challenges, and then tomorrow we should go into luminosity on the blackboard if I manage. I'm not sure. I didn't do that for decades. And then I also realized that there is no specific RF lecture, and RF is still important. So I will try to do my best, and I hope my RF colleagues at CERN will bear with the quality of what I do, which is okay. Okay, so first regarding the context, these are a number of projects that have been discussed in SNOMAS. So just to show you that there is plenty of different projects. There are high sorts of large rings with E plus E minus colliders or hadron colliders inside, or even electron proton collisions. As you may have heard, the FCC proposed for Europe, located at CERN, or CPC followed by SPPC in China. So these are the two competitors. There was actually also a proposal of a really large proton ring that would be located in what now some call the Gulf of America. So the Gulf of Mexico, sorry. Okay. Then there are linear colliders in different flavors, either with superconducting or normal conducting technology, with cold copper, which is normal conducting, but at relatively low temperatures, or using plasma with recirculation. So there are many, many different options. I don't want to go into that. The muon collider, which is quite compact, as you can see here. And then here you have the wake physics, right? So this is way too much. So what are now the colliders discussed in Europe? And as you certainly are aware of, last week in Venice, there was the Open Symposium of the European Strategy. And so we are all fighting about that. I think there's maybe not a huge surprise. So in Europe, there is a plan A, which is likely going to be the future circular collider, which I still believe is an interesting name to have future in the name. Which would be a E plus E minus collider ranging from the Z to, well, at the moment, actually, the real proposal is 240 GeV. There is the potential to upgrade to also produce the top. 240 would be for the Higgs. This part turns out to be a bit challenging, and then followed by a hadron collider in the same tunnel, like what we did for the LHC, which actually was the lab tunnel before, with the order of 100 TeV. Obviously, the big risk and that part is the cost of the overall project. It's not so much the technology for the E plus E minus, or for the hadrons, the magnets are challenging. You will hear more about that from Luca Butura. Also, China might go ahead with the CPC. They have a choice now. They could, if they get the money from the government, and they will certainly be able to implement a E plus E minus collider with such a tunnel. I think there is no doubt that they have the capabilities for that. So that's why we need to have a plan B. FCC may be too expensive. Maybe we cannot have the big tunnel, or maybe CPC moves forward. And so there are a number of options discussed for plan B. There is CLIC and A plus and minus linear colliders, initially at 380 GeV, can go up to 3 TeV. Actually, currently we consider 1.5 TeV. The 380 is because of the top. You also get the Higgs for free, so sort of with that. The muon collider, which only was initiated a few years ago, 3 to 10, well, that's what I will present. LHEC, using the LHC to collide with the electrons, or lab 3. You just put a new lab into the LHC tunnel and make it more, go to somewhat higher energies, so you can even cover the Higgs. So I will not say much about that. If you, we can see if there's discussion time at some point. And then there are many other linear colliders. Now in the US, basically the statement was from someone said from the P5 that there should be no Higgs factor in the US. They are happy to have it offshore. Somebody else takes care of it, pays for it. And instead they want to focus on the 10 TeV center of mass, parton center of mass, which could be a 100 TeV proton collider, or a 10 TeV muon collider, or E plus and minus collider. There is a strong so sort of people like the muon collider there a lot. Actually, when the P5 came out in the New York Times, it already talked about the muon collider, so they got the message right away, even if it was more carefully phrased than that. And I will show the National Academy supports the muon collider in the US very strongly. Japan, they are still hoping to have the ISC funded linear collider, but I think, okay, not so much is moving. And China, obviously, it's a matter of the Chinese government to want that or not. I mean, if they want to show off, they can have that. They are certainly capable. Okay. So what are the factors? Let's be very simple. Obviously, for the physics, you are interested in the particle type, the collision energy, the luminosity, and the background conditions in the detector. And then there are the things that are less fun to a certain extent, which is whether you can have a site, what the technical risk is, what the cost is, the power consumption, environmental impact, and support by society, which all goes there. Now, unfortunately, this part is as important as the other part. I mean, you need to have a good physics case, but you also need to be able to convince people to pay for it. So when I was young, I preferred also to work on that, but we have to take that into account. So the physics case, this will be made during the week much better than I can do it. So I just want to say that in Venice, it was partly visible, unfortunately, maybe not as strong as it should be, because the muon collider physics reach is included in a number of the studies. But maybe the best way to see that is the National Academy of Science has actually made a statement now about 2 weeks ago, where here you see the members, quite distinguished members of that committee. And they stated that a collider with approximately 10 times the energy of the Large Hadron Collider is crucial for addressing the big questions of particle physics and making discoveries. That the 10 TeV muon collider on the Fermi National Accelerator Laboratory site would have a similar discovery reach as a 100 TeV proton collider. I suspect also if it's located elsewhere. But this is a really important statement because people were questioning, is that really like a similar reach? But okay, they believe it is. And then a muon collider combines the advantages of an electron-positron and a proton-proton collider with a much smaller size. So very strong support there. And for the rest of the week, you will get more. For those that are not particle physicists, so there is some accelerator physicists. Also, obviously, the reason is that a proton-proton collider, because it's like bags of particles that one collides, has only a fraction of the energy of the protons available for the physics production. And also, you don't know the initial conditions very well, while in an E plus minus or mu plus mu minus collider, you have well-defined initial conditions, and you have the full energy of the collision available for the physics. Just to mention, there are also some people entertaining the notion of a photon-photon collider, but I will not say much more about that. But it's actually fun to design. So now what defines the energy limit? This is not very surprising. Typically, we have circular colliders where you can accelerate the beam in many turns, and you can collide it many times in the detector. So here we have only one detector, but there could be more. We have the RF there. Now, the thing that will happen is that a charged particle on the curved trajectory is actually emitting radiation, synchrotron radiation. And that radiation goes with the energy divided by the mass to the fourth power and 1 over the radius per turn. So that's the energy loss per turn. And already LAB had a loss of almost 3 GeV for 100 GeV beam. So like over 30 to 40 turns, you would have lost the full energy in the beam. I mean, obviously you replace it, so stay there. So that gives a limit to E plus E minus circular colliders, because the synchrotron radiation now becomes worse and worse. It does not limit protons very much, because the proton has 2,000 times the mass. So you can easily find that it's some 10 to the 13 times less radiation. So proton colliders actually are limited by the magnets that keep the beam on the circular orbit. Now, to avoid that, probably you have linear colliders, which just don't bend the beam. That's all very well, as you can see here. So you produce a beam, you accelerate it, and then you collide it. And you can only collide it once, obviously, because you cannot bend it back. So that solves the problem. That's why we have so many linear colliders. But obviously, it has some challenges of its own. Or the other solution is we can use a heavier lepton in the circular collider, and the muon, being 207 times heavier than the electron, actually has much less radiation, synchrotron radiation. So that's great. The problem is it has a lifetime of 2 microseconds. Otherwise, it would be totally straightforward and boring. Okay, just this is to illustrate how that works in practice. This here is from the last European strategy. I didn't see so great plots of comparing very thoroughly things this time. Maybe I'm prejudiced because this is from a presentation I did there. So here you see the luminosity of circular lepton colliders coming down dramatically with energy. It goes with a little less than the 4th power. So, and then you see linear colliders here, and you see that actually the luminosity that here is proportional to the RF power, and it does not depend on the collision energy. So it goes up because you use more RF power. So that's very nice. So in this regime, you need to have a linear collider. Here you can use a circular collider. And obviously, muon collider would be interesting in this regime there. So what is the principle? I don't think I will say too much, but there are limitations of linear colliders. So first thing is you need to produce a beam here, and you need to make it very cold, very, very dense. And you do that in a damping ring. The damping ring, we will see the same for the muons. Basically works by producing synchrotron radiation. So you have your particle with a momentum and longitudinal transfers. You radiate synchrotron radiation, which takes away transverse and longitudinal momentum, and you re-accelerate. By that, you reduce the transverse momentum in many turns. Then you squeeze into the main linac, so you have some connecting piece here. You accelerate the beam, and you squeeze it very small in the detector to get high luminosity out of that. And this is because the luminosity, or the beam size, which I will show is proportional to 1 over the luminosity, goes as a function of the lattice of the design of the magnets here and a beam property like that. So that's why you need to squeeze the beam here and produce a cool beam there. Producing positrons is a little more difficult. You send electrons into a target and you collect positrons after. Okay, so that's a principle. And the challenge is obviously to get high luminosity out of a single collision. And also you need to get the full energy into the beam in one passage through the main linac. So for the muon collider, there was some evaluation of the promises by something called implementation task force during the SNOMES process. So that were senior physicists of different specialty that looked into assessing how these projects could be expected to perform, how they what one could expect as cost and power consumption, based in part on what the projects provided, and also using some relatively complex scaling formula based on experience from past projects. So like for the muon collider, we provided exactly 0 information, because that was at the time when we had just started after last European strategy to do something. And also we wanted to see what comes out. And what you can see here is, first of all, why was the muon collider interesting? This is a 10 TeV muon collider. This is the LHC, this is FCC, and click at 3 TeV. And you see, actually, the bigger ring here is the accelerator ring. I will come back to that. This is similar to the LHC. It's actually very close. So well, you can already guess that we will try to fit it in here. And it shows how compact a muon collider is as compared to other projects, which showed sort of lead to a reduced cost. Here you can see a 10 TeV muon collider. They predicted had a similar cost, well, even somewhat less than click at 3 TeV. My hope was that we would be roughly similar. And then there's an interesting feature that if you look at the plot before and you normalize the luminosity to the beam power in a linear collider, this is constant. That's also why plasma colliders are not going to beat things. They may be cheaper than something based on copper, but they still have to face this limitation. So the luminosity per power is the same, while in a muon collider, as I will show tomorrow more, the luminosity per beam power goes up with energy, provided technology can do it, which is just great. Okay, so this is, again, cum grano salis. This was a scaling, and now we do better. Okay, so now the competing options are a linear collider with 3 TeV for going to multi-TeV, the muon collider with 10, and FCCHH with 100 TeV, roughly being the same. And you see that the muon collider could be cost effective. Maybe it's the same here. But if you want to go to 10 with click, you would roughly have to triple the cost. And with HH, actually, the cost estimate of HH seems to be quite low compared to the scale cost that the implementation task force finds. So you can think why that may be the case. There is some. Okay. So let's go into the muon collider. So the muon collider, the one that we study, we also looked into a different design, actually, but the one we study uses protons to actually produce the muons. And you can see here, you have a LINAC where you send actually H minus. So it's ions. I mean, it's protons with 2 electrons. Come back to that in a moment. Then you accumulate the beam in a ring. You compress it to very short pulses. We need 2 nanosecond long pulses, 5 pulses per second, and send them into a target. In the target, you produce pions. It's just you send protons at a target, lots of junk coming out, in particular charged pions. And the charged pions have a tendency to decay to muons. They're very close in mass, and so with a very high probability, they become muons. Now you have the muons, and you put everything into a solenoid so that the muons are all going forward because they have different charges, plus and minus, and different energies, and you have to collect them. Now they move forward, you then actually bunch them. So you try to longitudinally define where they are because they, with different energies, they just spread out. So you compress that longitudinally, and then you send them through a cooling system, which is in matter, and I will not say very much about that. I have a short thing. Chris will explain you everything you need to know about that later in the week. And it's fun. You cool things in matter, which normally you cannot because you would get sort of particles would get stuck there. Then you go through a system of LINACs, recirculating LINACs and fast ramping rings to bring the beam up to energy. Obviously, LINACs initially because it is limited in length, so you want to get to higher energy early because the higher the energy, the longer the lifetime. It's proportional to the energy. It's gamma times 2.2 microseconds. And then at some point you have to compromise for cost. You cannot have a LINAC for 5 TV. Well, you can, but you pay a lot. And so that's why you go to recirculating LINACs and rings. So the trade-off with cost becomes more relevant towards the end. And then you injected full energy into the collider ring, which you make as small as possible using high field magnets. That's how that works. One thing in all accelerator presentations, you will find that there are 2 important technologies. And it's just because the particle is charged, and so it's sensitive to electric field and to magnetic field. Magnetic field bending it sideways, basically, an electric field bending it, or sort of accelerating it. So with this equation, you already get a feel for what are the relevant technologies. I should say even a gamma-gamma collider is like that because you have electrons that go to the collision point, and then you make photons. So it's all electrons. And so obviously, you need RF cavities, RF technology to accelerate the beam, and you need magnet technology to guide the beam. So Chris and I will say something on the RF. Luca will cover the magnets. And then because of the muons decaying and then leaving a high energy particle, roughly on average with 1/3 of the muon energy, it's actually a broad spectrum, an electron, a positron, you also have to shield the components from that. So shielding is also important. So Anton, Daniela will take care of that. So this is just to say, spoiler, those are the key technologies. The cost is in the magnets and the RF and also efficiencies. Cryogenics is related to that, machine shielding. And then you have all the other important technologies, and people would be really upset if you say that it's not important, but they typically are not the cost drivers, or they don't drive the parameters in such a critical way as these 3. Okay, that's why people focus on them, which is a bit unjust because like vacuum technology is totally interesting once you get into it because it's really, but okay. So this is the luminosity scaling before we go into the technology. Tomorrow we will discuss it a little more. It's a fun formula. So the luminosity, if technology does not stop us, is proportional to the beam energy, the magnetic field of the collider ring, the energy spread we can tolerate in the collider ring, the density of the beam, so the charge divided by the transfers times longitudinal emittance, and the beam power, so the rep rate with which we inject muons into the collider ring, the charge of the bunch, the number of particles in the bunch, and the energy again. So this is beam power. Okay, and we will go into that tomorrow. But here's just some parameters to show you how that works. So this here is site independent, and then we have 2 sets for CERN. So here, like, let's look at the 10 TeV collider. So we have a relatively high bunch charge of almost 210 to the 12 particles, which is 10 times what we would have in high Lumi LHC. It's 2 times 10 to the 11 there. So it's a very high bunch charge. It's a little less at 10 than at 2 because obviously at 3 TeV, because obviously some muons will die getting from this energy to there. The transverse, okay, I have promised with Microsoft PowerPoint. So there should be a transverse here. So the normalized transverse emittance is 25 micrometer, which is about 10 times of what you have at the proton collider. The LHC has something like 10 times less. The bunch length is actually 5 millimeter at 3 TeV, and then becomes shorter as we go to a higher energy. And it goes as 1 over the energy, verify that. And the beta function is proportional to bunch length. We will discuss that later. And so this means that you can squeeze the beam more as you go up in energy. So the luminosity per interaction point you can see here. The integrated luminosity that we aim for the physics is 1 inverse autobahn here and 10 there. This is time that we need to achieve that. This is because they wanted us to give that time. And there's always +2 because the first 3 years count as 1 because you need to ramp up. FCC does that magically, very rapidly, but in practice, LEP needed like 4 years to get to full luminosity. So we assume it's 5, but then 25 and 70% or so for the first 3 years, and then 100%. And the circumference of the machine, and you see the circumference obviously increases as we go up in energy. And here you see the fields we assume in the dipoles that bend the beam, the collider ring. And you see that we use a different technology that's more available nowadays, even if it's not really that thin. And then we go to HDS later on, which allows us to get to a higher field and so make the ring relatively less big. I mean, it doesn't scale with energy fully. And here in these scenarios, for example, at CERN, we would even consider using a big tunnel initially for this energy, which compromises luminosity. We get fewer collisions, but would allow us to use niobium titanium, which is the technology of the LHC, which is very cheap, relatively speaking, less than $1 billion for that ring, and which could be quite attractive. But it compromises the luminosity first stage. Okay, so some advertisement on the collaboration, because we want some of you join if you haven't yet. So formally, the kickoff meeting was in 22. We started actually preparing that from 20 on. It's currently hosted by CERN, and the goal is to have it co-hosted also by Fermilab in the US because they are interested in that. It has 61 members that sign, so institutions that sign the agreement, and a number that contribute work without having signed, and some that are in the process of signing. I mean, it's fine if people do work without voting rights. Signature is important for voting rights. Currently, it's mostly in Europe, but this US contribution is strong and it's increasing. They were just a little late with their strategy process, sort of compared to Europe. And it answers some requests. The last European strategy, so 18, 19 had actually demanded that we look into the muon collider. The European Union gives us money for design studies, so we have to answer them. And the US has these recommendations to look into that. It's a global engagement, and to show that here, the recommendation from this National Academy, the first recommendation was the United States should host the world's highest energy elementary particle collider around the middle of the century. This requires the immediate creation of a national muon collider research and development program to enable the construction of a demonstrator of the key new technologies and their integration. Very strong statement. Now the idea, there's more recommendations, is to do that together with Europe, because we would like, at least inside of the collaboration, to maintain this also as an option for Europe. And then we will see who gets the funding to build. There was also this submission from the US community to the European strategy, where they actually clearly spell that they need funding, funding is needed in the US and in Europe, and the close collaboration between the two regions is important, and also contributions from other regions of the world would further strengthen the program. So a very collaborative approach. So indeed, we try to do the R&D together, and then at some point we might fight funding. Well, the funding agency should fight for who gets it, but that's a bit in the future. These are the partners in case you're interested. So you can see if your institute is already there, and here you see these are US partners. We have quite a number of IFN partners, and the UK is also very strong. Okay. So then just for formalities, we submitted to the European strategies. So they want a short document, which we did, some questions that we answered like everybody else. And then we have a 400-page document, which gives you all the details, maybe more than you want to know, signed by 450 plus people. So there you can look up all the things. We are still polishing the long one. And our aim was to indeed have some initial stage by 2050. Okay, so let's go into the key challenges. There's the physics case, but I think that's taken care of by the physicists, that they're all enthusiastic about it. So that is, well, it's not a no-brainer because brains are put on that, but it's going by itself. Then there is some dense neutrino flux, which comes from, in particular, the interaction regions. I will talk about that because when the muons decay, they produce neutrinos and they go into small cone, and normally they shouldn't produce any problem, but they do a little bit. Then we have the beam-induced background, because when the muons decay, they produce these high-energy electrons or positrons, carrying on average 1/3 of the energy of the muon, and we have like 40,000 muons decay per meter in bunch crossing before the detector. So you have to make sure that the debris doesn't go into the detector, and Anton and Daniele will cover how we get rid of that. But those are fundamentally things that are really critical. And then we need to look into the cost and power consumption and risk of going to high energy, because that was new compared to the US studies before. To really scale, they were looking at maybe going up to 3 TeV, and we wanted to have 10 or something. That makes also a difference, because the muon collider at low energies is not so competitive because it's higher risk, more difficult. But to high energies, it is the only game in town. And then certainly to improve the beam quality and look back into what has been designed before on the muon production. We were resource limited, as you may say. We had a very small budget, and basically we got much of the contributions as voluntary contributions, even people saying like, oh, I can do that over the weekend or during my vacation time, because formally their percentage was very low, even not sometimes zero. And so we focused on the key parts of the machine. And the key part is driven by either it is very difficult to design, the lattice, the magnet lattice, or it contains technology components that are critical. So DOE, following NASA's terminology, calls it critical technology elements. So that means things that are very important for your project and that are not like things that you believe can be done based on experience with other stuff before. So it goes beyond the state of the art. And so you have to carefully identify them. And we see, for example, the compression of the protons to these short pulses is one of them. The survival of the target. Before we had looked into liquid targets, so can that be done? The cooling system is such, and then we have magnets and RF cavities that are really critical for that. The ramping to very high energies, we believe that, I mean, the cost and power is to a large extent driven by the RCSs here and the collider ring itself, including the machine detector interface and the neutrino flux and magnets. So these green areas were the ones that we focus our studies on, and we would like to complete the studies connecting everything. But priorities, I mean, you have to look first at the most important things and then look at something else. That's a general lecture. People will always tell you, you should have looked into that as well. And then the only thing you can say is, yes, should I not have looked into this other thing because of that? And then typically they say, oh, no, no, no. Okay. So one thing that I will be light on is that since the muons decay, transmission is critical. And this here is an old table from last year. It shows you the number of particles in the beam as we go along the machine. We start with 500 10 to the 12 protons that we send in a bunch that we send into the target. That produces 45 10 to the 12 muon pairs, so it's mu plus and mu minus. Actually, mu plus is more likely. We have more mu pluses, so we look at the mu minuses. That has to do with the charge of the proton being positive. And then, as you see, as we go along the system, this number decreases by like a factor 30. Actually, the goal is to have 20% more, so we need to improve the systems here a little bit. And so that shows you that making things very quickly, making the cooling very short, accelerating really rapidly the beam is important because indeed this is one of the key drivers of our design. Okay, and you can also make the fun calculation: how much proton energy do you need to produce one muon at the collision point? And you see it's a 1.67 TeV muon pair, and so you can compare to the energy of the pair there, and you see that the proton energy is less than the energy that you have put into the muon. So it's a perturbation of that, which is good. Okay. So detectors will be very short. There are two detector concepts that are being studied, which is great because it shows that there's interest. We even have two. One is called music, which was started by INFN. Also, the other one is called Maya, which I think the US and DAISY are driving at this moment. I should, again, emphasize that the Maya is the daughter of Atlas, which tells you something. Maybe I should not mention so much that I think she committed suicide at some point. So to be verified by somebody who remembers Greek story more. And actually, Atlas had many, many daughters. She is one of the 7 he had with the player, and there are more daughters. I mean, okay. But it's very nice, and I think it's very healthy to have two, because it gives you more flexibility, and you can follow different approaches, and you really have a little bit of competition also in thinking. It's very good. Beam in use background, again, you'll get the full lectures on that. Just here, it's about 40,000 muons per meter in bunch crossing that you lose at high energy. At low energy, it's more muons, but they have less energy. So it's like 500 watts for 500 watts per meter all the time. I mean, the total energy per meter is roughly the same. And 1/3 goes into the electrons and positrons with a broad spectrum. And then you have the 2 neutrinos, this is decay. And now you have to shield your detector by putting these masks. So the interaction point is here. You have all of this junk coming from there, and you catch it with this mask and protect your detector. And actually, if you have decays inside of the detector, it's less important because the particles, I mean, the electron positrons tend to go the path that the muon would have taken. So they go out on the other side and create trouble down there. And you will learn why that is not important. But overall, I think the conclusion is we can do the important physics with this background, but we could do better without the background. So there is improvement potential, but it's not the showstopper. So which is convenient. It means people should really work hard on that, improving it. Just to say, this is a fun thing. I mentioned that there is less synchrotron radiation than with E plus and minus, but there is suppression of all sorts of secondary effects, like incoherent pair production plays a role, but it is reduced by the heavy mass of the muon, less beam strahlung because the muon is heavy, less virtual photons because the muon is heavy. We have less coherent production of particles, which at click at 3 TeV is already important, and the trident cascade, which could actually, if we would collide with this energy, electrons and positrons, this would be a huge factor of destroying particles or taking away their energy. And in the muon case, this is not so important. But I will not go into detail. So let's follow now the beam from the beginning. First thing is you start with the LINAC. And actually, it's not a proton LINAC, it's an H- LINAC, as I said. Simple reason. You want to collect the protons in this ring. And if you inject protons into a circulating proton beam, that doesn't work. There's something called Liouville's theorem, which you cannot put particles with the same quantum numbers in a way into the same phase space. It just doesn't. So the trick is you have H-, you send that into the ring where you have the circulating protons. You have a foil or you use a laser, and you strip off the electrons from the proton, and then it can circulate nicely with the circulating protons. So by that, you avoid violating Liouville's theory. Great. So you collect them here, and then you compress them in the next ring. And then you send them to the target. And I think this looks very good at this moment. The main question is, do we need 1 or 2 bunches, which we combine on the target? Okay, I mean, maybe it can be done with 1. So this it's very interesting. And we feel that this proton complex is nicely on its way with the 2 megawatts that we want at 5 GeV. And now becoming greedy, we say, oh, could you also do more power so that we would have some reserve? Usual thing. And nobody's ever satisfied. Everybody should be equally unhappy and should go equally challenged possible. Okay. So then you send them into a target. And there are 2 things with the target. If you send in the protons, the target itself, in our case, is a rod of graphite, 3 centimeters. Right, so you can see that here. And so you get a shock wave, I mean, because you send 400 kilojoule within 2 nanoseconds into the target. And graphite is very nice because it's very robust. And actually, it is a funny material. It is a material that becomes stronger, cracks less as you warm it up. That's why it's used, for example, in jet engines and tanks for some reason. I'm not exactly sure where you use it there, but I remember that some Russian firm that 30 years ago or so sold some graphite to us, obviously. Normally would have used that for tanks. So now it seems that the target can survive. So there are simulations that look into the shock that we have in the target. And then you get the next problem. You get spray because you get all the shower and so lots of particles from the proton beam come out on the side. You have large angles. And what you want is that the target here should be in this strong magnetic field, the solenoid field, because the solenoid has the tendency, any particle that moves forward, no matter what the charge is, will spiral in the solenoid and so will continue to move forward. So great. Strong solenoid, and to keep the beam small is something like 20 Tesla. Now, the problem is 20 Tesla means a superconducting solenoid, and yet now you have all of this junk coming out on the side. So what have you do? You have to shield your solenoid from this junk. So you put a thick layer of tungsten here and there, and by that you capture the power. And this, on the other hand, drives the aperture of the magnet. So the solenoid becomes more and more difficult the bigger it is. And Luca will explain exactly what the problem there is, but we believe that we can do this with high temperature superconductor. And so it seems possible, the magnet people tell us. Then you have to check for the shielding itself, if that's okay. How much debris still goes into the solenoid? Will it destroy the solenoid by radiation or create a heat load that is too high? And all of that looks fine. And then you have the problem, some protons will not scatter. It's not so likely. And they will come out with full energy at the end. And you have to get rid of them. And you should, so you need a path for them as well. Okay, so this is the design. And in order to increase the power, maybe we can still use graphite, or we use liquid metal, where you have like here, sort of a curtain of liquid metal coming down, liquid lead, to because in that case, you don't destroy the target. I mean, it's liquid. You just have more liquid coming after. And so you can, in principle, take more power. Tungsten powder can also be used. It looks like a liquid. And I can show you, I have that. Sorry, I got the order of the slide. Just to show you that we did an experiment ages ago at CERN using mercury, which nowadays you cannot use anymore. So that's why it would be liquid lead. And here is C. So you have here a liquid mercury jet. You have your beam hitting longitudinally this. And this is how the experiment looks like. This is the mercury jet before the beam comes, and this is how it looks like after the beam comes. It looks pretty bad. But the good thing is this explosion happens slowly enough that you don't care. The beam is already gone. And then like the mercury explodes afterwards. And it recovers to this state quickly enough. So mercury would have been a solution, but then for safety reasons, it cannot be used. So since I mentioned the magnet, I will not say much about magnets because Luca will. But just for those that are not familiar with superconducting magnets, there are 3 groups that are of interest. The first is niobium titanium, that you operate at 2 or 4 Kelvin typically. That is the technology used for the LHC. And that has limitations in the field that you can get 8 Tesla roughly in the LHC. Maybe you can get a little more, but that's roughly where it is. So this is a known technology, well developed. Then you have niobium-3 tin, as you can see here, which is operated at the same temperatures, either 2 okay. 2 gives you better performance, 4 is easier with the cryogenics, so it's always a trade-off. You can reach higher fields with that. FCC-HH was hoping for 16 Tesla, but it's a difficult technology. You need to have these things in your hand, and then you realize that mechanically this is very difficult. You put it in place in tubes, and then you heat it up. And it's very expensive at this moment. Actually, there are not many uses. and not many producers, so the cost is slowly going up. But it's, for example, used in high luminosity LHC for a few individual magnets that are put in. And then you have high temperature superconductors, which can operate at higher temperatures, maybe up to 20 K. I mean, in principle, it's like a gliding scale. And they can even achieve higher fields. And typically, they are made like tapes. So it's like a flat, thin thing. And actually, the superconducting layer is very, very thin on that. This here is Repco. It's one example. So you see this here is the support, and this here is the actual superconductor. And more than 30 tests have been done in solenoids with that. It's very difficult to do it in dipoles. But so for us, this is the most interesting technology because it can achieve the highest fields, and we want to have very high fields to squeeze the beam everywhere. And also because it operates at higher temperature, which means that losses are easier to cool away. If you remember Carnot inefficiency, if your base temperature, the low temperature is 2K or 20K, to cool, you need a factor 10 less to cool down to 20K. If not so clear, we will mention that again with the RF part. Okay. So, and now just to say, look, I will come back to that. We have magnets all along the system, and basically we try to use HTS wherever we can. And we have all the conceptual designs for that. So that's in a good shape. So, okay. Now, after the target, we have these muons coming out. You will bunch them, but I don't know, Chris, if we will discuss that. Maybe that's already too detailed. So now you have to cool them. And the cooling principle is very straightforward. You cannot use a damping ring because, first of all, there's little synchrotron radiation, and then it takes a long time, so milliseconds or so, and no go. So what you do instead is you cool them in metal. So you have a block of an absorber here, and you go through the absorber, and now you have ionization, and so you lose momentum through ionization. And it's, again, the same thing. You lose it in the direction of the particle motion, so you lose transfers and longitudinal component, and you re-accelerate afterwards, and so you reduce the transverse component of your momentum in many small steps. So you need to have many of these systems, one after the other. Okay, that doesn't work with things that get stuck in material, like electrons would start producing showers, protons would do that. But muons, they don't like matter as much. They don't care. They do that for a long time. This here is the formula for the transverse effects. Now, the cooling comes from reducing the momentum of the particle. Then there's a nasty effect, which is multiple scattering. You see the nuclei and also the electrons of the matter, and your muon gets transverse kicks from that. Okay, and that's the multiple scattering. For detector people, this is what you have in any layer of your detector. I mean, you go through a certain radiation length, I mean, fraction of radiation length, and you get a certain transverse scattering from that. And this is given here. Now, Chris will also introduce beam dynamics, so bear with me. So now, how important is the multiple scattering? And that depends actually on something that we call the beta function. So this here is the beta function. And this beta function is smallest if the solenoid field is highest. So we put everything in a solenoid. The stronger the field, the solenoid, the smaller the beta function is, the less important this heating term is. You'll get the detail later, but that's how it goes. And so we need, therefore, to put the target into a high field solenoid to reduce the multiple scattering, the heating term. That's the whole miracle. And now that makes life complicated because, especially in the 60 cooling, and then sort of in the first part of the cooling, we want to make the cavities be very close to the solenoids for compactness, and then that creates trouble. Okay, so first of all, this principle of cooling has been demonstrated in an experiment called mice, which you can see here, where more or less you had individual muons coming from the left, and you had a solenoid here, and then you had an absorber or a place where you could put an absorber or not. And this here was the distribution of the muons before. This is the action, so like amplitude. And then after the location of the absorber, if there was no absorber. So the green one is what you get if there's no absorber. Now, what you put in is some absorber. Liquid hydrogen is the best. Actually, the ratio of multiple scattering to cooling to deceleration is the best for liquid hydrogen by a good factor. So you put that in. What you see is the incoming beam still has the same distribution, so here. But after that, what you see is that you have more particles with smaller amplitudes and some reduction in the higher amplitude part. So particles at a larger amplitude actually were convinced to go to smaller amplitudes because of the absorber, as we discussed before. So that's what happened. So this is a proof of principle, and I'm sure Chris will give you much more on that. Now, for us, what is very important is to get the emittance. And in the formula, you saw longitudinal and transverse emittance. So here you have a plot. You have the horizontal emittance there, the longitudinal emittance here. And we start on that side from the right. So the beam goes this way, not like that way as it does in the rest of the plot. And so you start with a very hot beam from the target. You cool it in this type of cells that we get more. And at some point, you actually have a train of a few of these bunches. You put them together. And that means you have to increase the size of the beam because you have to put them side by side or one after the other. And then you cool them further. And then at some point, you start running and you actually let the longitudinal emittance grow again, and you still cool in transverse. And we will discuss later why that is a good idea. But to get here to smaller transverse emittances, there is one thing that you have to do. And that's the following. If we take the luminosity formula from before, then we get an equilibrium emittance. So that's the point we would adiabatically move towards, which is this one here. And so you see, first of all, here there's the magnetic field. The larger the magnetic field, the smaller the equilibrium is, because the less important multiple scattering is. This is the energy loss per unit length. And this here is the radiation length. So it's the energy loss per radiation length that matters also, that we want to maximize. And then here is the gamma, which is close to 1 and all of that. So now there is a feature. This here is showing the energy loss of a muon in matter. And as you can see, typically we operate in a minimum ionization part here. So all the energies of the muon beam are decelerated in the same way. Now, for this one, if you go to lower muon energies, then actually the loss is increased. So this term is increasing, which is very good. And so we get more cooling. We get a smaller emittance because the cooling becomes more effective. There is one obvious problem with this, which is that in this regime, a high energy muon is decelerated less than a low energy muon. And so the energy spread that we have in a muon beam increases, and there's nothing we can do about it. Okay, so what we have to do is here we have to let the longitudinal grow in order to get the small transverse emittance. So we take that and we try to do it as late as possible, and then we try to run to get the transverse quickly enough small without heating the longitudinal too much. But in the end, it turns out that we cannot profit from a very small longitudinal emittance. So in any case, okay. So that's the principle behind. Here you can just see what is the equilibrium. Obviously, we want to have one that is below our target emittance because we only adiabatically can reach that. And here you see the magnetic field and the energy of the beam, and it shows you as the magnetic field in the final cooling increases and the energy of the beam decreases, you get smaller and smaller transverse emittances. So we want to be somewhere in this regime, like with a 40 Tesla solenoid, we need a beam energy of 10 MeV or less. Okay, so that's, but Chris will show you that in more detail. So there's a trade-off. Okay. Now, what is the problem with the technology? First, normal conducting RF doesn't like to run in a high magnetic field. So sorry, I just trying to see where I'm. Okay. So half an hour. Okay, that should be about fine. And I'll show you why. But RF cavities are always limited in the field, in the accelerating gradient you can have. And basically, I will show that superconducting cavities have two limits. For normal conducting cavities, basically the limit is that the cavity makes bang and has a short, and the energy in there goes berserk, and the beam actually gets a kick. So we cannot drive the cavity to the gradient we want, but the gradient is limited. And there are some theories of exactly what the limitation is, but in reality, you have to measure. You cannot predict so well. I mean, you have some experience that tells you where you are. And so operating the cavity in a high magnetic field is a concern. Come back to that. But it has been demonstrated for 2 different approaches. I show that. So we have designs of how the cavities can look like. We have designs of magnets for that. These are actually the final cooling solenoids. So at a very high field, and look, I will show. So we leave 40 Teslas. The next step should be there, and 55 might be still possible, but that will take more. And then we actually realized that, for example, if we have a really cool muon beam and we send it into absorber, so we have a muon beam that's very, very dense. So it can punch a hole into stuff. That's obvious. And first is the windows. So we have like liquid hydrogen. We put it between 2 windows. And now what can happen? We can evaporate the liquid hydrogen. That's not a good idea. So towards the end of the cooling, we actually move to gas as an absorber, because the gas will get a pressure rise, and we can tailor that by tailoring the density of the gas. If we have a very dense gas, the pressure rise will be more than if we have a not so dense gas. And then we have to also make the window that maintains the gas survive. And here is a test done at CERN in smoke. And there you see how the window looks like after sending a proton beam through it, which actually has a much higher density than what we would have in a muon beam. And it's still, I mean, it held, but it looks a little sort of taken. So we need to obviously do more experiments on that. So now here, what is really relevant is to measure RF in magnetic field and to measure absorber survival, which we can do with protons. Then we have the 60 cooling cells, which are very compact. I will not say so much, Chris will do. I think we have many different types of cells. They all look different. Here we have large apertures, the lower fields, and then as the beam emittance goes down, they become smaller, and we need to reduce the equilibrium emittance, because basically if we are below a factor 2 of what the beam has, then we are fine. So we reduce it like that. And here we have designs of how to engineer actually putting an RF cavity inside of these solenoids, as you can see here. And there are huge magnetic forces between the solenoids, so it's a big problem. And the cavity needs to be connected remotely, because you cannot see that. I mean, you basically stick the cavity to connect here, and you have to do that without seeing what you do. So there's some remote paths. So that technology is being developed, and it's quite exciting for the engineers doing that. I thought I had something on the RF. Okay, I think it's in the RF lecture. So sorry. I go back to the what limits the field of the RF in the solenoid on Wednesday. So sorry, I saw it here. Okay, now after the cooling, we go through the Linux, but I will not say something about that. And now we go into the rapid cycling synchrotrons. And so first thing is, what is the ramping time that we can afford? And it's of the order of a microsecond to 10 microseconds. For the first small ring, it has to be faster. It's roughly a similar number of turns in each ring. And then it can be slower for the later rings, where we are at higher energy. So ramping magnets in 10 to 1 or 10 milliseconds. If you compare, like the LHC ramps within 20 minutes. Superconducting magnets don't like to be ramped rapidly. They get eddy currents. You need also to put in a huge amount of energy into the magnets to get the magnetic field. So no way. Okay, that leaves normal magnets, so copper windings. And because that typically consumes power, what you do is you use iron to help you. So you put, here you have a typical magnet, you have the copper part here, and you have iron, which reduces the field inside of the iron. Obviously, there has to be the gap, which you cannot fill with iron for the beam. Okay, so we are now limited to using normal magnets with iron, and the iron can get up to about 2 Tesla field, and then it starts to saturate. And in practice, we say 1.8 Tesla, because it becomes nonlinear at 2 Tesla. So the magnetic field in our fast ramping magnets is limited to 1.8 Tesla. That's the reason why the accelerator ring needs to be way bigger than the collider ring, because in the collider ring, we can have magnets with 14 Tesla or something. Here, we can go to 1.8. And then I will come back to that on the next slide. Also, the stored energy in the magnets is quite large, so we have to recover that. It's actually a nice exercise. You can just do the integral over the free part for the beam, B squared, and you find that we talk about some 200 megajoule or something. Now, there is one trick that clever people yes, came up with to improve the situation with the fast ramping magnets. You mix them with cold superconducting magnets. And you do that in a way that the superconducting magnet bends the beam, where when you inject, bends the beam inwards, and the fast ramping magnets bend the beam to the outside. You have minus 1.8 Tesla. Now you inject the beam, and now you start ramping down the normal magnets as the beam energy increases. And so they subtract less and less from the effective magnetic field of the solenoids in a way. And then you start to ramp them up to help the superconducting magnets. So basically, you change them from minus 1.8 to 1.8 Tesla, and therefore you almost double the swing. You don't quite double it because you have the cold magnets that take a bit of space. Okay, so by that, you get twice the reach, but you get obviously a very horrible orbit. If you would ramp all the magnets together, then you get the same orbit turn by turn. And what you get here is you get something where you bend the beams. So at low energy here, this is always one cell. You bend the beam to one side, and then you increase the beam energy. So if you're in the middle, then basically you go straight. And then as you ramp up to full energy, you bend the beam like that. And by this, you get different orbits for each turn, but you can maintain the beam on orbit. This here is within a single cell how the orbits look like. So this is when you inject. And as the beam energy goes up, the beam starts to follow that orbit. And you have to make sure that you have enough space horizontally to accept the beams when they circulate, okay? So that's a trick to basically half the cost, because you can half the size of the ring. But it's challenging and inconvenient. Okay, so now let's look at the actual design. And the first thing that you worry about, I think we'll come back to that then, even if you have a lattice, is the energy that you have to give to the beam. And that is, as we will see on Wednesday, it's a very high bunch charge. So if you have an RF cavity, the bunch will take out energy from the cavity. And depending on the energy stored in the cavity, obviously, that can be an important factor. Now, what we would like to do is use high frequency RF, so 1.3 gigahertz, which I have here in the conclusions, which are the ISC type cavities. Now you can calculate that you take out something like 10% of the energy with a single passage of your bunch through the cavity. I mean, it's just the amount of energy that is put into the beam. So that doesn't sound like it's easy to maintain the energy spread of your beam if the first particle and the last particle see a field that's different by 10%. And so I was very doubtful that we can use the 1.3 gigahertz. I was told that this is possible, but I didn't believe it. Now, there's one trick that you can do is in a ring, you can let the particle move longitudinally. So turn by turn, it is at a different location longitudinally. And that helps. And the other thing is you have some voltage that compensates in part of that. So you don't operate on crest, but you operate, your beam arrives somewhat before you reach the full field. And so this rising field compensates to some extent what you have. But this mixture longitudinal is still very, very important. And it turns out that indeed, it seems that if you do enough longitudinal mixing, you get a beam that has an energy spread that's acceptable. What you have to do is in this case, you cannot have just one RF station around the ring as normally, and you would do that. But you need to spread that. You need to have a few, because your longitudinal motion is so rapid that if you had only one per turn, then you would not be able to sample that correctly enough. There's something like Nyquist's theorem. So you need to have enough stations so that you can sample the longitudinal motion of the beam well enough. Let's maybe come back to that on Wednesday. Okay, so we can use 1.3 gigahertz RF. That's amazing. Here we have the aperture of the magnet. We have lattices of all of them. And we start now to actually see how we can get through the lattices. So this was the initial attempt when we studied all of the 4 RCSs in a row individually. And you see this is the longitudinal emittance. So it's the growth of that. And you see that we almost doubled it. So we solved the problem for the one ring, and we sent the beam to the next one, and so on. And the beam grew longitudinally enormously. Now, we started to actually adjust the one ring to the next. So to get the phases in a way that we get a smooth transport, and you see that indeed we get a smooth transport, and we get only a very small emittance growth of a few percent. And that, I think, can still be further optimized. So with this, it seems that we are capable of accelerating the beam with known relatively inexpensive RF technology. If you go to a lower frequency, more stored energy just means things become bigger and more expensive. I mean, that's how you get more energy. And so using high frequency is good. I think we'll see that. Now, I said that there is a question with the magnets. And so if you do the calculation, you find that you have like 200 megajoules in your fast ramping magnets to get the field, the 1.8 Tesla, to make the beam go around. So now, if you would put in 200 megajoule 5 times a second, that's a gigawatt. So we would use a gigawatt just to have the magnets ramp. And actually, for the ones that ramp in 2 ways, it would be double that. That doesn't seem like a good idea. I mean, we have a much lower power consumption. So okay, what do you have to do? You have to use power converters. And these power converters, they store energy in capacitors, like so. And what they do is they then put the energy into the magnet, and then they recover after the magnet is sort of did its duty. They recover it back into the power converter, and there's a little loss on the way, but the goal is to have this like be of the order of 1% or 2%. And that's not very easy. In particular, I know, please don't ask me to explain it. Maybe I manage, but maybe not. If you change the sign of the magnet, you also typically would change the sign of the voltage in the capacitor. And the capacitor doesn't like that at all. It dies very rapidly if you do that. So they found actually a clever way of how to not have that. So you can have the voltage in each capacitor only going one way and still change the direction of the voltage in the magnet. Okay, this is explained here, and I'm not sure I managed to explain it myself. So they came up with this design, and they actually found the following numbers. So like if you would have a RCS, let's say in the SPS, the first stage, we have more than 4 kilojoule per meter stored. And then we have some losses, a bit in the iron, a bit in the copper, which is 1.1% of the stored energy per cycle. So that corresponds to less than 2 megawatts for the full ring operating at 5 hertz. And here you see similarly in the LHC, where we would have a single-sided, so just ramping magnets ring first. We talk about 13 megawatts, and then we have a second ring there where we change the sign of the ramping magnets. So the efficiency, so the loss is relatively more important, 6%, but actually divided by 2 because we put in the energy twice per cycle. And so this is a total of 40 megawatts, which is needed for the fast ramping magnets. And you see that if we had missed the target of 1% or 2 by a factor 10, if it had been 10%, we would be still talking about 400 megawatt, which is way too much. So this is ingenious. This we need to build. These magnets, something like that, doesn't really sort of is not used normally in an accelerator. So very nice design, very clever, and I think the cost went just down by $500 million. All of the magnets. So you see, I mean, we talk about really high costs. I will not give you, by the way, costs for components because it is not on the slides, because you should never do that, because otherwise industry will at some point figure out what they are supposed to cost. Okay, so that is an ingenious thing. So after the fast ramping magnets, we go into the collider ring, and there we have a lattice design that is challenging. We need to protect, now we have the same problem as in the as in other places. The muons decay, and actually when they decay, we produce something like 500 watts per meter of high energy electrons and positrons. That would hit a superconducting magnet, and that would need way too much cooling power because we need like a factor 700 more to cool. And so what we do is we protect the magnet with a thick shielding from the decay of the circulating beams. So you can see that here. I don't know, Anton, I didn't check. That's probably not in your presentation. Okay. And so we keep that roughly at room temperature or slightly below. So the cooling is very efficient. And we have only like 1% of the total power leaking into these superconducting magnets. That's great. However, the magnet now has to be big because it has to contain the shielding. And that makes it more challenging. So we have conceptual designs, and Luca will explain what the consequence of that is. But we have it here. We have the cooling design. And we also looked at the mover system that I will come back to in a moment. Okay, so this is challenging. Now, there is one thing on the final focus that we will discuss with the luminosity more. As we go up in energy, we said we make the band shorter and we want to squeeze the beam more. And so the squeezing system on the focus system is basically two lenses. You have the interaction point here. So you have a lens with a short focal length. It's actually 2 or 3 magnets, but forget about that. It doesn't really matter. Imagine one lens here, the short focal length. This is the collision point. And then you have another one for the circulating beam, which is a long focal length. And you basically have an almost parallel beam here, which you then focus to this spot. So it's small here, and then focused into the interaction point. Okay, so that's the principle then. I don't know whether you will touch that or not, but that's standard transformation. So this is like what they call a minus I transformer, because something that's plus an offset becomes minus an offset, just for the factor in between. Now, the problem that we face with this is that as we squeeze the beam to a smaller size here, it becomes larger in this lens. This is for the FCC, so I had asked for that years ago. And here you see that if we half the bunch size transversely at the interaction point, it doubles roughly in the magnets. And so the ability of making magnets that are strong enough and provide enough space becomes critical to squeeze the beam at the interaction point. If at some point, the larger the magnet becomes, it needs to maintain the same increase of field with offset. So the larger the pole tip field becomes and the more challenging it is. And then there's a limit of how far we can go. So but that seems to be in order. And we have the magnet designs for this, for the circulating beam with tests. And we also have something that's quite interesting. We have systematic predictions of what these magnets can do as a function of the field that we would like to have and the size of the magnet. And you see here is, so the larger the size, the smaller the field. So this is something I cannot use, and this is the area that can be used. And obviously we try to stay close to the boundary for efficiency reasons. Okay, and Luca will explain that. So we have that for all the magnets, which is quite exciting. And you see that with the apertures that we need for the shielding, we can have a bit less than 5 Tesla with niobium titanium, something like 11 with niobium 3 tin, and maybe 14 with HTS. Okay. Then I will not say much about collective effects, but they are obviously very critical, because with this very high bunch charge, if your particles fly along, you will interact with the environment. You produce electric fields that can feed back on the beam, and Elias will discuss all of that. So just to say, we looked at that certainly for most parts of the machine, and there, where we looked at it, it was not a problem. It is something that has to be considered for the first part of the cooling. We'll give some limitation there, and Elias will explain you what that is and how that works. But it's not like we didn't look at it. Okay, so then let's come to the placement, and that's a little annoying as a subject, because when your muons decay, they produce 2 neutrinos, and they go into a very small cone in a forward direction. And you should not expect them to create a problem, but our goal is to have a negligible impact on the environment. Negligible has a specific legal meaning in that sense. And that requires that you cannot have this very dense neutrino beam coming out of the ground just like that. So you have to do 2 things. You have a problem coming from the interaction regions where you go straight for a while. So you get particularly many neutrinos going in one sort of a cone in each direction. And you have something coming from the arcs. Now, from the arcs, it is very narrow, some 20 microradian or so open angle. So what you can do is you can deform your beam line very slowly vertically. Every few hours, you change it a little bit. And by that, you change the angle of the beam in a substantial way, and so you dilute the neutrino flux. And we believe that is okay, even for the Geneva area. Now, for the straits, it is more difficult because you should point to something, and you maybe put some little experiment there and the fence around it. And that in like Geneva, okay, I was very worried about that. But here you can see an orientation of such a ring, which is there. This is drawn in a way that you cannot see all the detail, and we would come out in the Jura in some down going slope where nobody is living, like this. It's no, well, I think I know roughly where it is, and in the Mediterranean Sea where nobody's living. So with that, there should be an orientation that's fine, and radiation protection is working on giving exact numbers and checking with legislation so that this is fine and that we indeed have a negligible impact. So with that, now we were looking into how can we actually put such a, where can we put such a machine? And here you see potential implementation at CERN. Fermilab, that's probably, it's somewhat less developed, so more work will be done there. But we try to see how that would go. This is the collider ring that would be consistent with the placement. And then we would start with a beam where there's LINAC 4, maybe use the space that was foreseen for SPL in the past. So there was a 5 megawatt proton LINAC foreseen already a long time ago. And then we would send the protons through the SPS tunnel into the Prevson site. So everything that's gray is CERN land. And then we would have the actual target here. We would have the cooling, the initial acceleration, and then send the beam into the SPS tunnel where we would have one RCS. Then we would inject into the LHC tunnel where we had one RCS and a second one. With one, we would go to 3.2 TeV center of mass, and with two, 7.6. 10 TeV would require more ambitious technology. It's not excluded, but this is what we are developing right now. And then we would inject from the LHC into the collider ring here, and the experiments are on CERN land or very close. This land actually is something that CERN wants to reserve, so I think the civil engineers put it there on purpose instead of on CERN land. Okay, so that looks like we could basically reuse everything at CERN, and we would need just some cut and cover tunnels here. This is the design they had, and the civil engineering would be fairly cheap. Okay, so it can be done. Then we have an evaluation of the cost, even if that's, well, it's not so boring, unfortunately. So you have the cost scale here. Carlo, who did the cost estimate, he doesn't want to give a number, so he gives a graph. And there's a red line in the graph. That's the most likely value. But it's uncertain because we didn't do any optimization also of the complex. We took it as it is, and we looked at the cost. There's uncertainty in the elements, but there's also maybe potential to improve things fundamentally. Okay. And this is not so different from what the implementation task force came up with. Okay. Cost drivers, just to be very quick. You see that actually RF is very important. This here is RF. This is others. This is civil engineering. The color is a little hard to read, but this is RF. So RF cost is actually very important. Then we have the solenoids, and we have the other magnets, which includes the collider ring and the fast ramping banks and the power converters. So this is the total for magnets. This total for RF. So you see the main share. And typically, civil engineering is similarly expensive, but in our case, it's not. And as we go up in energy, again, it's still very expensive here. For the RF and for the magnets, including solenoids. So it's roughly like 50% of the cost for magnets and a quarter for. These are uncertainties for different technologies. So we need now R&D to reduce these uncertainties and hopefully realize the cost reduction. And Luca will probably come back to this. One of the things that we had in there is we have these scalings, what the magnets can do. So again, the magnetic field and the size of the hole in a magnet for different costs that you see. By going to lower cost, we compromise the performance, but it could still be worth it. While if you push the cost, we get higher performance. And so obviously there's a huge trade-off to be made between the design, wall design, luminosity versus cost and so on. Some fun to be had for the future. For the power consumption, there's also an estimate. This here is the power that we would expect to need during operation, 117 megawatts for 3.2 and 182 7.6. This is more certain than the cost number because it's calculated. There's some residual error, but it's not so enormous. There's, as I said, the big uncertainty. Most of the cavities, so we can scale from existing cavities. So for the IC cavities, we just need to adjust the pulse length. And I mean, we have all the formula we need to calculate how much that would use as power. For these fast ramping magnets, we didn't, and now we have it, and we need 40 megawatts for that. So that we use the conceptual design for that. So that looks quite good. And here you see how that looks like along the system, and you see the proton driver. As we expected, is sort of, well, still 70 megawatts to produce 2 megawatts of beams. So you see it's 12% efficiency roughly. The cooling, 12 megawatts, that's okay. The initial Linac, so this is the biggest one, 10-ish. The RCSs, indeed, they stick out. The collider ring, and there it's a funny thing that at lower energy you need more because you operate at 4K, but now in titanium. Well, here you use HGS, so actually the heat load goes down with the energy, so it becomes cheaper. Okay, and then general electricity for ventilation and things like that, and so that's 20 megawatts. Okay, so that's what it is, and you see that indeed the RCSs are the main driver as we go to high energies. And then here, just very rapidly to show how that goes according to specialities. So this is the RF in the RCSs. You see that's a bit more than 40 megawatts. This is the cooling of the RF, which is about 20. So that's 60 altogether. And then you have the magnets, which is like 40. So still the RF in the RCS is more important than the magnets. Not by a huge margin, but that's why I thought we should have a little bit of discussion of RF in this school. Okay, then we come to the plan for the future. Okay, I think I was supposed to be finished by 45. Good. So this is the timeline that we submitted to the European strategy. It assumes, so it's ambitious, it's the most ambitious timeline that we have, which assumes firm commitment to build the muon collider as the next thing after Halumi in Europe. Okay. If that's if somebody chooses that, is another question, but I mean, if the CPC moves forward, that is something at least that should be considered. There are other scenarios where like Europe builds a muon collider after a Higgs factory, or the US builds a muon collider. They may be a little more stretched. And you see here in this scenario, we need to do 10 years of R&D, and then we would prepare the project, and in 41 or so, construction can start, and then in 50, the operation could start. This is, by the way, consistent with the comparative document from CERN. Even if everything here is T0s, T1s, and T2s, but you do the calculation and you find that if a decision is done instantaneously between two phases, it just works. The R&D program, so that's the bit for the next 10 years, is given here. It has work on the accelerator because we need to finish the design and optimize it. As you can see here, it has the muon cooling technology as the most novel and unique thing that needs to be financed with the demonstrator and tested. It has work on the detector, 900 person years. It's a huge contribution, but to improve the potential. And then the magnet program, which is also important, and where actually we see that industry is very interested in that. So we see that like fusion reactors and the solenoids, that's very synergetic. And industry, I think, is threatening us to give us money for that part. Not all of what we need, but part of that. So this is just to show that this is an ambitious but possible scenario. I think, I don't know if Chris will show that. This is for the cooling technology, the most involved one, where we need to actually test cavities in a magnetic field. So we need test stands, and actually SLAC is building the first one. They will be ready by January next year. Very good. I think they were, so INFN and the UK also tried to build one, but I think SLAC is now ahead. Then to build a cell where we test the RF in a magnetic field with power, then a module and a demonstrator where we actually produce a muon beam and send it through some cooling cells. And then we would ramp that up to have more deceleration, more cooling. And you see that this would works. So we would have the first test with beam by 35, and then by 40 we would still have improved tests. And now we are looking at sites. So there are some at CERN that look promising, and Fermilab has budget to actually make a site study for the demonstrator location as well. For the way forward, we first need to implement the R&D plan. There is a part that is already financed from the past, and then we hope to get more resources. So one of the important things is now we will have a task force to actually prepare the sharing of the work. So that's typically say, this is great work, but then you have to become concrete. So you have to sit around the table and say, who is willing to do this and who is going to ask his boss if they get the money? And then, okay, then it goes back and forth. So that's an important part of the process. And so that's starting now. And with the US being active, it's very good because we can share and, between Europe and US, the overall effort. Still need central funding through CERN and Fermilab, if possible, and see where we can get money in addition from the European strategy. There are synergies that we want to exploit with other physics, trainer physics, and so on, and with the societal applications. So these are fusion. These firms or institutes are interested in fusion, and they were, I mean, you probably recognize that there is a station somewhere out there, because everybody understands who gets the first fusion reactor is big in business. We have Infineon because they do power diodes that are important for the power converters and also for the green grid, because the green grid is not stabilized automatically. It needs to be stabilized with diodes. Because typically the grid is stabilized by all the rotating turbines. So if you use more power than is on the grid, then they slow down, provide kinetic energy into electric energy, but that doesn't work with the green grid, with solar. But you see that also this HS technology can be used for for power generators for windmills, offshore windmills, to have the green side, and there they can be operated at a higher temperature, and you want big units that are maintenance free because they are offshore, so it's very hard to fix anything if it goes wrong. Okay, so we hope that this turns into something useful. Okay, so we are making very good progress and people are extremely motivated. We have a global R&D program proposal that now needs to be funded, and our advisory committee actually reviewed us, now it's last week, I mean, two weeks ago, and they strongly recommended, I said they were impressed with the progress that we make. And they see this as an extraordinary technical opportunity that we work on all the important things. And now we should launch and support a muon collider, muon cooling demonstrator and test stands as soon as possible. You see the members there. You see that we got even some like experienced project leaders of biggest science projects in the past. Okay, for those of you that want to connect, well, we have a website, and anybody is free to contact our secretariat to get an MOC to his institute. It has the institute as the sign up to become, for the institute to become a member of the collaboration. Okay, and I think, yeah, that's it. So I don't know. Doesn't leave question, but I think I started also a little later. So
Perfect.
I'm happy to answer anything, and if not, there is also a discussion session later.
Yes.
Today, but still.
In the afternoon, we have a time for discussion, but yeah, that's a good occasion for quick questions. I get away from the speaker. Maybe just for my own curiosity, can you tell us again the picture of what goes on in the rapid in the RCS?
Yeah.
Because I see you have different stages. I'm in the wrong place again. So just for a cartoon-like picture, what's going on?
Okay. Okay. So first thing, if I forget about the hybrid solution for a moment, because that's just a neat additional feature. So what happens is you operate your magnets at a low field, matched to the incoming beam energy, and it goes around. And then as you increase, so as you accelerate the beam with the cavities around the ring, you ramp up the magnets in parallel. So the beam stays always on exactly the same orbit, and the magnet strength just compensates the beam energy change. Now there is, ideally, actually, we would have one big RCS for everything, starting from the lowest energy, bring up to the highest energy. And for practical reasons, that is a little more difficult. There is something that maybe can squeeze in tomorrow, that you need a certain rate of acceleration of the muons to not lose too many. And at the first order, this effective RF gradient does not change with energy. If you want to double the energy of the muons for a specific percentage of loss, you always need the same RF per unit length. And so a small ring and a big ring have the same, the same effective RF gradient. If the ring is bigger, you just need proportionally more cavities around the ring with the same voltage. Yeah, I don't know. So the synchronization between the RF and the the gradient in the cavities and the magnets is important. Initially, we thought that the magnets would like to swing, like a sine-like thing, which normally in a synchrotron you would do. But the RF doesn't like that. The RF, it's like you switch it on, and then you have the beam, and you continue to accelerate with the same rate. And so they had to make some trade-offs, which in the end they did. So there is some work between the RF experts and the magnet experts to find a common ramp-up scheme that is good enough for both sides, which is relatively linear. The way it works in the magnets is you have all of this energy stored in the capacitors, just charge them. And then you basically let it flow into the magnet where it starts to, where the current creates the magnetic field. And then at some point you stop feeding that, and then you sort of the current is coming back, and you capture it again in your capacitors. I think that's a very simplistic description, but maybe that's good enough. Otherwise, one has to look at the diagram, how that exactly works. And this, what you lose on the way is you have nonlinear effects in the iron. You have potentially eddy currents in the iron. So there's some heat. The iron is heated up a little bit by that. That's a loss. And the copper cables also are not perfect conductors, so you lose something there. But that is all taken into account with this 1% loss. So that's the main reason for the loss. The capacitors themselves are very efficient. I don't know. For the cavities, I will explain in the RF lecture that what you have to do is they're empty initially. You have to first get the gradient in it. You have to get the accelerating field into it, which means you have to put RF energy into it. Okay. We will have that on Wednesday. So you start filling them, and then every time a bunch comes by, it takes something out, and so you have to keep filling them at the rate at which the bunches are going to take the energy out. And that then defines all the properties that your cavity has to have, as we will see on Wednesday. I'm so sorry. I will explain a bit better then. I don't know if that answers the question, or
I think it's very much more clear now. But just for curiosity, you have this plot where you have the percentage of longitudinal emittance.
The growth.
The growth, yeah.
Yes.
It looked like it was a success already, that one. But
yeah,
is it true? Optimized has reached a level that you cannot. You can consider as a good result already.
Yeah.
What's the situation?
It's like always. It's important to give the expert. We have really great people doing all of that, but basically for almost everybody, this was new. So to think about what the requirements are for the muon collider, it was very hard. And as I will also explain on Wednesday, one thing is you with this beam loading, what you do, okay. So typically, if you want to accelerate a beam, your RF does this. This here is 0, and so you put your particle at the phase like here, and you get the maximum field that accelerates in this direction, okay? So this here is the gradient, the voltage, and you put your particle, so there is a sinusoidal oscillation, you put it at this moment. Now, if you have many particles here, let's take two. So this one takes out energy from the cavity. It's accelerated, so it takes out energy, or it leaves a wake field. I have a slide where I show that this is the same thing. So this would be seeing less accelerations. So it would get, after some time, if you did that, then here you have a graph and you have the energy. This particle would have a higher energy and this would have a lower energy. And that's obviously not what you want, especially since we want to keep the energy spread out. So what do you do? So the first thing is you say, this is bad. I'd rather accelerate the particle here and there. Okay. So this doesn't see the full voltage. And this sees something more, but minus what this one took out. Okay. So now obviously you put them at a stage where, maybe this here is a little exaggerated, but what this leaves is a reduced field. And so that the field, the effective field that this particle sees is the same as this one. Okay. But if you would have no beam loading, so if these had very small charges, this would obviously now see less energy than that one. So what would happen is that this particle here would move up to here. Okay, because it always sees more field than this particle. However, as we said in the previous one, this was reducing the field, the amplitude. So what it does do is it still reduces the amplitude, and you just choose the part where you are here in a way that it happens to put this particle at this location. So they get the same, to see the same field. Okay, that's roughly what it is. So now in practice, that's not so easy because it's not just a simple linear dependence, but that's the principle. And if you, now the RF people always think in terms of power, and I don't understand it. So the way you could see that is you make the same thing and you have two oscillations. One is the one that you want for the acceleration, and then you have a second one that is 90 degrees out of phase. So they add up in quadrature. You don't, and they we have a different color. Okay, and again, this here is the right, and the other one you put in a way that it. Let's do, okay. My freehand drawing qualities are really limited. So this is the same thing shifted by 90 degrees, and it's, here it looks green, here it doesn't. Okay, and so this one will accelerate a particle that is a little earlier, more than a particle that's here. Okay, and this reduces this one, and you can just match the two. So what the people did is, they said, this compensating part of the wave and this accelerating part, we have the same amplitude. It's running at 45 degrees, or actually 135. Okay, so you're running at the moment when your wave is just having this nice slope. Okay, and you can do that for each ring, but then you take the beam as it comes out of the one and put it just into the next one, and it doesn't really work so well. So what you have to do now, you have to play with this phase and voltage on all of the rings, so that you get always a good transfer, and that how the beam looks like at the end of the one ring nicely matches into the next one. That's a little more advanced RF. It's pretty straightforward. Okay, so that's what you do. And that's what made the longitudinal, because otherwise you can imagine if how much you take out here and the slope, if they are not matched, then you still get an energy spread, right? Nothing guarantees you that this slope compensates the reduction of the field from this particle. You have to make it work. So you have to choose the parameters so that they work. And then it's okay. That's not a law of nature that having these two waves is solving the problem. Maybe we try on Wednesday. Okay, start halfway.
Any other quick question for the end of the lecture? I don't see any. So let's thank Daniel once more. We come back at 2, possibly. Lunch is ready, don't worry.